University of Arizona is developing a software factory for the new software engineering degree. Now, what is a software factory? Before the adaptation of what is called the DevOps pipeline, software was typically built by one team, made up of developers, and deployed into production by another, made up of operations. Modern software development best practices have merged the two teams into one cohesive unit in order to optimize the transition from development to deployment. A software factory expands beyond development and operations to include initial requirements gathering, modeling, and project planning. In order for software engineers of today to be competitive in the workforce, they need to understand what writing code, automated testing, and building scripts for a DevOps pipeline looks like. The goal is to design and develop an online web-based platform for software engineering students to access systems development lifecycle software tools. In the early stages of the project, we met with our project sponsor to develop functional requirements. This functional block diagram provided by our sponsor was the primary source of direction for our requirement development. We gathered 35 system requirements under 7 major categories made up of availability, value, environment, performance, security, tools, and deliverables. We then grouped these requirements into subsystems represented by our system block diagram.
Our system is divided into 2 types of software tools. Standalone applications, which are largely accessed through graphical user interfaces, and continuous integration, continuous delivery, automation infrastructure, which are largely text-based development packages. The first group allows students to design and develop their code, while the second allows for testing and deployment to be automated for consistent reproducibility.
Through the creation of our system block diagram, we divided our project into 3 primary MVPs. MVP 1 would be the selection of the cloud environment that the software factory will be hosted on. MVP 2 would be the selection of the system development lifecycle tools that would populate the cloud environment. Finally, MVP 3 would cover the final implementation point design solution.
The team began its decision-making processes by conducting trade studies on the types of web hosting service providers available. Private cloud hosting services such as Amazon Web Services, Google Cloud, and Microsoft Azure were compared. Midway through this process, another option presented itself, using the College of Engineering's own high-performance computing network. Additional trades were performed, and the HPC was deemed as the most appropriate for cost and accessibility purposes, among others. After the hardware had been selected, the tools that would populate the software factory also needed to be selected. We compared 3 options for each tool section, judging along the criteria of open source, ease of use, and popularity. The final selection of tools included of project management using Open Project, requirements analysis using open source requirements management tool, software design and modeling using Draw.io, version control using Git, IDE using Atom, Python unit testing using PyTest. These tools would be the primary ways of students to interact with the software factory. Once the integration and implementation phase of the project began, the team encountered compatibility issues within.
Once the tools were selected, point designs were considered for the integration of the tools. The team decided to use software tools of Open On Demand and Docker running on the cluster CentOS Linux operating system to run and host the tools natively on the HPC. Open On Demand is an HPC management tool developed by the Ohio Supercomputer Center, which provides job scheduling and terminal access to the HPC. This provides web access for students to access the tools and as many of the HPC nodes as required. Docker is a service for containerizing applications so that they can be run on demand. They contain the minimum requirements to run a particular application. The combination of these 2 tools allows us to run the software factory natively on the HPC.
Change requests. During the integration phase, the team encountered multiple issues including high-level scope creep and low-level compatibility issues between software tools. The project underwent 2 major requirements changes as well as a revision to the implementation point design. The team realized the scope of the project was too large to implement in its entirety and shifted a number of requirements from a threshold to objective, keeping the relevance to the future system. Testing and results. The team developed a number of end-to-end user tests to ensure each system requirement was satisfied. These included testing login, logout functionality, authentication, and each of the tools' installation on the HPC. The team recruited freshman honor students to assist in the testing process to assure the software factory functioned on a number of different operating systems and web browsers. The refinement of our test procedures revealed that there were limitations to the number of users able to be served and browser incompatibility issues.
Let's look at an example of using the system. The user first directs themselves to portal.engineering.arizona.edu. Here they are met with the UA WebAuth authentication screen, where they must log in with their NetID credentials. Currently, the portal only supports NetIDs from within the College of Engineering. Upon login, the user is brought to the portal homepage, where they are met with the message of the day. From here, they can access interactive applications, a file system, a job scheduler, a terminal, and a virtual desktop containing all of the installed software factory tools. Let us first explore the interactive desktop in one of our tools, Draw.io. Here we can access a Linux desktop environment where we can open our tools, create files, and save to the file system. Draw.io is a system modeling and flowchart creation system. This is one example of the types of system lifecycle development tools necessary for students to build complex systems. Upon logging out of the desktop environment, we can return to the Open On Demand file system, where our saved diagram can be accessed as well. The team learned an incredible amount, from developing a full-scale software solution to the Linux system administration. Our work was largely exploratory, searching for constants in an undefined space. Through our work and our mentors' efforts, the project was able to collect $500,000 in additional funding to continue the development of the platform. The scope of the future work has also increased, with the end goal being the newly named Digital Transformation Factory, which will expand to include additional engineering majors, researchers, and collaborators. We hope future teams will continue our work in integrating the software tools into the Open On Demand's interactive apps. This has been an overview of the Team 22012's Engineering Software Factory. Thank you.